Welcome, welcome, one and all, to this organic chemistry introduction screencast brought to you by me, the thermodynamic mechanic. Some may call me that, some call me other things, but to get right to the chase, we are going to talk about in this episode, this exciting episode, hydrocarbons, naming somewhat, structures, and, don't mind the spelling, and a little more in organic chemistry. So, to get started, I suppose, and once again, you could follow along. You could listen to this. You could be walking to class. You could be in high school in between classes in your, 2-minute break between classes, or you could be taking notes of this. Be sure to pause along. I will stop occasionally for you to copy along because learning is most important. Or you could just pause the video. Doesn't matter to me. Figure out what works best for you. This is, let's get started. Okay, so organic compounds are just compounds with carbon in them. Carbon-based. Specifically, you might think of like hydrocarbons, so like if it's like CH, and then some number, or C to the N, and then it's, N. It'd be 2N plus 2 is the number of, that's a traditional hydrocarbon format. There's other carbon-based molecules like carbon dioxide, that's organic. Water, H2O, it's not organic because, there's no carbon in it. That's exactly what that means. So, I'm not going to stick on that too long, but just be sure if it doesn't have carbon in it, you can be sure that it is not organic. I mentioned this is a hydrocarbon. That's the formula for every carbon in a basic hydrocarbon. You have 2 more than twice that many hydrogens. We'll get to that in a little bit. So like if you have, let's just say C2, it would be H6, right? And I'm trying to remember the name of this with two carbons. Ethane. Duh. This would be like if you wrote it out, you have 1 carbon here, you have another carbon here, and then because all the bonds have to be filled because carbon can make 4 bonds, right? So you have the 1 bond between the carbons, but then you got to fill in the rest with H's, and that's where the 6 comes from. But these are both edge carbons, so they're on the outside. So if you really have a middle carbon, so like in propane, by the way, this is an expanded structural formula, which we'll touch on more in a minute. You notice for every middle carbon, because it's surrounded by 2, let's use a different one. It's surrounded by 2 carbons. So it can only make 2 hydrogen bonds. And that's where the whole, you multiply everything by 2, every carbon by 2 to get the hydrogens, and you add 2 because, if you think about it, every carbon has 2 H's, but the outside carbons, which you'll have 2 of, have 2. And that's just for standard hydrocarbon format. So, there are different ways to represent these things. This is the expanded structural formula. The condensed structural formula is like, this is a condensed structural formula. For propane, it would be C3H8, remember? And that's easy math. I didn't have to count them at all because, you know, you just take twice the carbon, so 3 times 2 plus 2 equals 8. Pretty simple. Hope you could do that math. Otherwise, you're going to struggle a little bit. Then we also have space filling model. This is to illustrate where the electron clouds can go, as well as what things are bonded to. And so basically, if we had a bunch of these molecules floating around, they would bounce off of each other kind of with that sort of geometry, and they would kind of like interact with that sort of geometry due to how the electrons and the hydrogens and the carbons, how they all kind of move around. That's advanced level chemistry. If you're interested, check out physical chemistry, advanced electron orbitals and all that stuff. But if you're not interested, skip that. Ball and stick, many teachers have, teachers, professors, students have little like plastic beads and little bars that you can connect to kind of form molecules. These are just a space and visual representation of, like, very similar to the space filling, except you can really see angles. That's the key part of this. You can really see the angles between different molecules when they're connected. These both represent methane, okay? These specifically represent methane, which is just C1. You don't have to write the 1, but it's CH4. Remember, you take the number of carbons, multiply by 2, so 2 times 1 plus 2 plus 4. Ooh, yeah. And it makes this sort of tetrahedron shape because of, you know, molecules have to fit in the easiest way they fit, which is to say they need to be as far apart from each other as they can be to fit kind of comfortably. And so this angle, which I believe is like 130 degrees, question mark. It might be 100, 104. It changes depending on the type of bond we're dealing with, but that's what the ball and stick is for. And then we also have skeletal structures. So methane, there is really no skeletal structure for methane. It's like, what, you're just going to put a dot to represent the 1 carbon? For ethane, so that's C2H6, remember. Ethane is 2. Methane is 1. Ethane is 2. Propane is 3. Butane, pentane, and these are all like, you know, you have an ane on the end. Pentane, hexane, heptane for 7. Oct for 8. Nonane for 9. And decane for 10. You usually don't have to deal with much more than that, although there's like dodecane and stuff like that, which I think is 12. I guess I could leave that on there for a hot second, but that is just the main carbon chain. That's dealing with the main carbon chain. But for ethane, like I was saying earlier, that's it. It's a single line is the skeletal structure for ethane, because each end point of a line represents a carbon, and you fill in the hydrogens that are required to fill in that carbon. So we have 1 line that means 2 carbons, and because they're both end carbons, they both get 3 hydrogens. And so that's where the dots get connected there. For propane, however, we would actually draw it like this. So we have 1, 2, 3 end points. End carbons get 3 hydrogens. Middle carbon only gets 2. And that's due to bonding. There's also something called Lewis structures, and that's where like you fill in dots. So a carbon has 4, dots for the electrons. A carbon has 4 electrons, but then you need to fill all of these. You need to make sure they all have a companion, if you will. So we have an H, and an H has 1 electron, so we can put it there. We have another H, it also has an electron there. We have another H, and it has an electron. We have another to make, say this is methane once again. Or ethane would be, usually Lewis structures are used for simple stuff like this. You don't really do Lewis structures for things bigger. So I don't know why I erased that. If you wanna copy it down, you don't have to. we're just going over all the different types of structures and ways of representing these bad boy hydrocarbons. Daddy thick hoss hydro. Okay. Yeah. And so there's one thing I haven't touched on yet. We've talked about alkanes, but what about alkenes and alkynes? Alkynes of carbons. So this is just everything is single bond. Everything is single bond. Ene means at least one double bond. Got that double trouble action. And alkynes means at least one triple bond. Triple James Bond. Okay. To represent this with ethane, so we have a C and we have a C. If we do a double bond, this changes how many hydrogens are on the molecule. This changes it. I have cheated you. There's only 2 hydrogens. Can you explain why? I'll give you a second. That's very good, correct. Yeah, because we have a double bond here. This takes away one of the extra bonds that would have gone to a hydrogen, right? And so a carbon atom can only have 4 bonds on it, traditionally. So we have 2 bonds with the carbons, and then each carbon only has 2 left to match up with their corresponding hydrogens. This is an alkene. Specifically, this is ethene. Or you could also call it 1-ethene. But that's a little bit redundant because there's only 2 carbons to go off of anyway. The functional group, this counts as a functional group, by the way. And we'll get into those as well. Those affect reactivity. Reactivity, what they react with, how often they react, and stuff like that. This is actually a low priority functional group. So as far as naming, it kind of gets pushed to the bottom. But if we can designate either of these carbons, either this or this, as carbon number 1. We don't, this is just for like a side note. We don't actually put carbon number 1 ethene. No, we don't do that. This is like just for helping us to label and name stuff. Carbon number 1, we could pick either of them because it's a symmetric molecule. Let's just pick this one. There is an ethene group on carbon number 1. So ethene group on carbon number 1, which means this becomes 1-ethene. But as I mentioned, because it would be redundant, because it doesn't matter which carbon we pick. Now, if we had it like this, if we had something like this, ooh, I'm bringing in skeletal structures again, which skeletal structures are the easiest and fastest, especially when you're fluent in this kind of stuff, to write stuff down. You can kind of visualize the spatial orientation with software is usually what's used, and a bunch of formulas that you don't even have to actually run a simulation. Rather, you just use the math to kind of make calculations and adjustments as molecules interact. But anyway, what do we have here? Well, we see there are 3 endpoints, so we know it is I'll give you a second, propane, or at least it's a prop type because there's 3 carbons. But we also have this double guy. This is a double bond, of course, like that is ethene, right? In skeletal form, to just basically an equal sign, ethene. This is propene. Specifically, this would be 1-propene, right? Once again, because the functional group, the ene, is on the quote first carbon, we always designate the functional groups of highest priority to the lowest number we can name them as. So because this is on carbon number 1, we have to pick it as carbon number 1 because it's closest to that. You know what I'm saying? We wouldn't name this like, we wouldn't start with this as carbon number 1 and be like, oh, well, the functional group starts on the second carbon, so this is 2-propene. That doesn't make any sense because we can have a 1 here. If we just flip the molecule around, we can have a 1 there. So that's why we name it 1-propene, but the 1 is redundant, so it's just propene. Yay! Everyone's all excited and happy because of carbon. Or sad and depressed because of carbon. You know, pick your flavor. One glaring example of this is also, you know, if we do this and we put it here, there's 4, so it's butene. But this double bond starts on either this carbon or this carbon. It doesn't matter, once again, because it's symmetric. So carbon number 2, we designate it because it's the lowest carbon, so this would be like 2-butene. Whereas if we did something like this is just 1-butene, but because the 1 would be redundant, it's just butene. So one final, you know, I mentioned it earlier, alkynes of carbons. Alkyne, Y-N-E, this is triple bond. And, you know, obviously with just CH4, methane, there can be no triple bonds because hydrogens can only have 1 bond and the carbon only has 4 to give. So, but with ethyne, oh, yeah, I know. This is a very reactive molecule. We only get 1 hydrogen on each because each carbon uses up 3 bonds with the other carbon, and so it only has 1 left to give to each hydrogen. And so this is just C2H2. Looks a little weird. Looks a little weird, but trust me, it's fine. Like I said, it's very reactive because, you know, the carbon doesn't traditionally want to be bonded to itself that much. I could go into the graphics and the detailed bonding of it, but that's, once again, check out physical chemistry. Yeah, advanced physical chemistry and orbital theory. So this is very reactive, especially due to heat, especially whenever you put it in with other kinds of compounds. Yeah, much more reactive than this, and this is much more reactive than just this. Butane, regular old butane. Once again, this gets naming priority, but it's a low priority, so I will double check on this, but I believe the yne is higher. No, it is not. Alkyne is actually lower priority. Alkyne is lower priority, so alkyne lower than alkene. So alkene has a higher priority in naming than alkyne. So if we had something like this, where it was like, on this side we have a double bond, but on this side we have a triple bond, well, what would this look like as far as carbons? I'll give you a second. You can pause the video here, or not. Pause and get a snack, good study snack, popcorn, gum, slice of ham, I don't know. Do you. So anyway, to pick up, we have 1, 2, 3, 4, 5 carbons, so we know it's a pentane type. And we have, this is either carbon number 1 or this is carbon number 1. Which do you think it is? And, you know, these are either carbon number 1 because that's where the start of the chain. Ignore that. That's the start of the chain of carbons. Okay, exactly. Very good. Yeah, so this is going to be carbon number 1 because the alkene is a higher priority than the alkyne. And so what this ends up being, and in this scenario, because we have multiple functional groups, you should add the 1. You should include the 1 for clarity's sake, especially if you're taking a quiz homework exam. You want to be clear on this. Obviously, check with your individual teacher. They might want something different, especially if it's an online format. But so this would be 1 dash een 4, because this is the start of 4. You know, we go 1 to 2 to 3 to 4. This is where the functional group starts. Yay. And then to 5. But 1 een 4 pentine. Boom. It looks a little weird, but that's it right there. And how this would actually look if we were to like draw out with hydrogen and stuff, on the doubles, I'm going to flip it around. Okay, we're going to do a 180 flip. This is going to be a carbon double bonded to a carbon with a carbon with a carbon with a carbon. This gets a hydrogen because it's an end. It's an end carbon, so we still got to fill it in. This doesn't get anything. If you notice, it has 3 bonds here and 1 bond here, so it's just by itself. That's very reactive. There is no barrier, if you will. There's no like hydrogen here that might push away other molecules. Yeah. And then obviously this would get 2 hydrogens because it, you need to fill in the bonds. This only gets 1 because it's double bonded here, and this gets 2 because it's an end carbon and needs its bonds filled. That's kind of how that would look in the expanded structural format. Yeah, pretty simple. Should make kind of a lot of sense. And we're moving on. We're moving on right along. This is kind of a long screencast, so if you stuck around this long, give yourselves a pat on the back scratch, ass scratch, head scratch, and relax. Take a few seconds. I'm gonna get some water. Oh, shit. Okay. All right. That hurt a little bit, but we're fine. On to cyclones. Cyclones. No, it's not actually cyclones. They're just like cycloalkanes. And once again, if I haven't been clear, an alkane is just a hydrocarbon. So like CO2, carbon dioxide, this is not an alkane. Fun fact. Not an alkane. Not guilty. The glove doesn't fit. But, something like I don't know, CH3OH. Yeah, this is a hydrocarbon. This is actually methanol. OH is alcohol. And this would look like just real quick. Right like that. So, anyway. I'll leave it. Screw it. Cycloalkanes, that just means there's obviously a loop. It's not just all sticks. There's a loop somewhere. And the smallest cycloalkane you can have is what is this? Give you a second. Cyclopropane. But there was a lot of strain. Okay. Thanks, Brian. There's a lot of heat. A lot of pressure on those angles there. And remember what I said about, carbons and bonds like to kind of orient themselves in a way that's easiest for them. Well, this is kind of like forcing it in, because like normal propane looks like this. That angle is a lot bigger than that little shitting thing right there. So this is kind of free floating. That's kind of forced in and constrained. So whenever you have stuff like that, that's almost a way of storing additional energy. And whenever you have something that's high energy in its normal state, it is more reactive, right? And like I mentioned with the triple bond thing. With the triple bond, that's kind of storing a lot of energy between those carbons. That's kind of, it's a high energy molecule, so, or at least higher energy relatively to other hydrocarbons. So it's more reactive. Cyclopropane. For each loop, for each, like, you'll notice, there's no end carbons, right? So these each just get 2 H's. So for cyclos, it's just CnH2n. There's no plus 2. That's gone. Bye-bye. Say goodbye to the 2n plus 2. And this goes up for, this is cyclobutane. We have 4 edges, 4 endpoints, so that's butane. Obviously, I'm drawing these because they're faster and simpler to understand, but I'm also kind of, adding, obviously, stuff like that. This, in just a regular format, this would just be C3H6, right? But you can't really tell that it's cyclopropane by just looking at that. You might say, oh, well, is there an alkyne or alkene group somewhere? Like, what how's it actually look? Because, like, if we had, C, that's 3 carbons, and then a C here, we can only add 2 more carbons. So if that's a 3, this can't be anything, and this can only be 1. Oh, so that would be C3H4. Okay, no, maybe make that a double. Yeah. Yeah, so that would be, this is the same thing, that essentially, right? We have C3H6. You wouldn't really be able to tell by that, and that's why I dislike that kind of format. Unless it has something like C double C2H6, something like that, which you could see, but I don't know. It would, an H would probably be over here, and it would probably be H2 and H4 or something. That's probably what it would look like if it was to be like that. And so, anyway, we'll just leave it. Why do I keep deleting stuff? You guys got to yell at me for that shit. All right? Tired of it. It's horse shit. Every time I try and erase this stuff, you got to raise your hand. You just got to call me out. All right? Okay. Once again, these each are going to get two hydrogens. That should make sense. It's cyclos. Yay. One specific type of cyclo is our friend benzene, and this alternates. This is like the standard chemistry molecule. Benzene, like the Mercedes benzene. Yay. This has 6 carbons, but also 3 double bonds, increasing its reactivity. So not only is it cyclo, so we have increased reactivity, cyclo and double bonds alternating, at least in the stick diagram here that we have, skeletal structure. So these each only get one hydrogen. Right? That's it. And you could tell that this is benzenes equals aromatic compound. Now, does this necessarily mean it smells good or bad? Like you left a washcloth in the bathroom for like 3 weeks without using the shower or something, and it just molds in there, or you light a vanilla scented candle. Those have aromas, right? Well, yeah. No, it doesn't necessarily mean that. Aromatic is just basically to describe anything that has a benzene. So if this, how we used an OH earlier, this could be an OH instead of just a regular hydrogen. And so this would be benzene all, I believe. So it'd be like 1 benzene all. That is a way to describe it. Don't fact check. Okay, no, actually, you should fact check me. It might just be benz all, but I believe it's one benzene all. You might not even need the one if we had this OH here. So aromatic, this is still aromatic. Let's go and smell the roses. Functional groups. A benzene also counts as a functional group, though, I should mention. Because, like, we could have this thing, and then on the end of it, this would count as that kind of, instead of, what am I doing here? Instead of, imagine this is all the rest of it. Instead of this being an OH, just make this benzene. And, just get good at drawing hexagons, I guess. I'm sucking, so ignore that. But okay, and that can work. And you could put this anywhere. Like this bottom part doesn't have to be. It could be down here, and it could be here. It could be around here. It's fine. It's fine. Yeah. So is a functional group. Other functional groups by priority. We got at the most prior, aka this takes, like, in naming, what carbon number do you pick? That's what priority is. I mentioned that earlier, but a little bit more in depth. Yeah, basically, if you have a high priority functional group, and a functional group simply means how it reacts differently than a standard molecule. A higher priority functional group gets to be on the lower number carbon. And so when you're naming it, if you see one of these functional groups, basically find the end of the carbon chain that's closest to the functional group of high priority. And one other thing on naming, I don't know if I mentioned this or not, whenever you have a carbon chain, you pick the longest possible carbon chain to name. So, like, if we had some random shit like this, and we had, maybe it goes this way, but then it also goes this way. But then it also, hey, you piece of shit, also goes like this. Don't mind the lengthening weird ass things. Okay, so what would be the longest carbon chain here? Give you a second. You don't have to name it, but just for knowing how to identify the long carbon chain. So, okay, let's just pick a side. We start here. 1, 2, 3, 4, 5, 6, 7, 8, 9. This is carbon 10, or at least from this angle, from this, how we're starting to kind of figure it out. So we'll just put number 10. You could look, you could see this is longer than this section right here. So that's kind of why, and this section. You can kind of exclude it. So then we have a few different options. We can go 11, 12, 13, 14, 15, 16, or we can go 11, 12, 13, 14, or we can go 11, 12, 13, 14, 15, 16, 17, 18. And so the longest carbon chain, even though this is pretty long and this is pretty long and it looks kind of goofy, we would use whatever prefix for 18 carbons. And on carbon 10, we have 2 off-shooting carbon chains. And these are also functional groups at this carbon. In a way, these are functional groups because they're not part of the main branch of carbon, the main chain of carbons. And this carbon, once again, it's connected to four. Yeah, this one, and then this one, and this one, and this one, and this one. It's connected to 4 other carbons, so it's kind of like it's under a weird kind of scenario and can react a little differently than normal. To name these functional groups, these 2 other offshooting carbon chains, we count how long they are from our center carbon, so from this guy, and we go from there. And we use this number 10, as in the naming. So like we start with this one. So 1, 2, 3, 4, 5, 6. So this is a hexyl. We add a YL. Hexyl. Hex because 6 carbons. Yl because it's an alkane functional group. This one is this one down here. It's 1, 2, 3, 4. So that is a butyl. Butyl group. But for 4, YL for alkane. And so this would be carbon number 10. So really it would be 10. I believe it would be, you go based on let's check here actually. I believe you go alphabetical. So it would be like 10 butyl, 10 hexyl, and then whatever the name of the 18 carbon alkane is. I should also mention, because these are alkane groups, they are very, very, very low priority. They are below alkyne. So here it is, the moment you've all been waiting for. Functional, I think I wrote this up there, but functional groups and priority. These we're actually going to we're going to pull up a chart that you can kind of look at because there's a lot to write down. So a chart for you to look at, kind of save and study and just really know. I'll kind of walk through it. So I'll see you in the next video. And by the way, stay fresh.